Hi everyone. I got the announcement a little late today because I forgot to post the announcement. I was sitting here waiting for time to come up and, oops. So I'm gonna let this run for like 2 or 3 more minutes. I'm gonna go fill my water and then we'll get started. See you in a bit. Alright. Probably not the best music to use for Thanksgiving. Probably should have used Resident Evil for Halloween. Still, it's kind of creepy to have this music playing and then just see still shots cycling through the campus that we can't go to. But, say la vie. Welcome back to Chem 140. This week, the only class period that we have is this one right now, today. There is no class tomorrow because the campus is technically closed, so all of the online courses are also not going to go on air. And Thursday's Thanksgiving, and you shouldn't have to do work on Thanksgiving, even if you're spending it isolated, which you probably should be. Whatever you choose to do, do it safely, but don't choose to do work. Take the day off because we need to recover and recuperate. Past that, what else is coming up? There is a quiz for units, I want to say it's 13 and 14. I can't remember off the top of my head. It's on a document somewhere. That's quiz number 8. That is due on Monday. That's a soft deadline, so get it in by Tuesday. That's fine. Lab number 4 is due next week on Thursday, December 3rd. Yeah, we're already in December. That still means that there's like 4 more years of 2020 to go. But hey, we're almost there. And the quarter is actually going fairly quickly, so hopefully being in attendance at the college has helped move things along a little faster than they normally would. That's really all I can think of other than things that are coming up past that, which would be exam number 2 is going to be during the first day of finals week. And then the final exam will be at the very end of finals week on Thursday. So that's just an outlook of weeks 11 and 12 coming up. There's also a lab number 5 in there. We'll talk about that next week because it's more of a, hey, we're going to do this together on Wednesday while I teach you stuff sort of assignment. So like you'll have all of that done during then. But more on that next week when we get to it. All right, so what are we doing today? We're doing stoichiometry. Stoichiometry is kind of the whole point of Chem 140. If you can make it here, you can make it 161 and 162, no problem. This is not really a new unit. It is more of a, hey, here, remember units 13 and 14 and all those calculations we did with moles and grams and particles and stuff like that? We can put all that information together and use chemical equations to represent that information quantitatively. And so that's what we're going to do here. So let me test the pen here. Oops, I didn't mean to advance the screen, but that's fine. I was having issues with my pen earlier, but it seems to have resolved when I rebooted the computer. Okay, so let's talk about this reaction here that I have on the screen. I have balanced this reaction. Sorry, there's something on my pad here. And those coefficients on there should be representative of a balanced chemical equation. So there should be the same number of nitrogen, hydrogen, and oxygen on both sides. You can double check that if you want. Now, if I do this reaction, what this is saying is that if I have 4 molecules of ammonia, NH3, and 5 molecules of oxygen, and I react them together, I would make 4 nitrogen monoxide molecules and 6 water molecules. So individual molecules would react in this fashion, but we don't really count individual molecules. That's too difficult for the tools that we have, which are macro scale. They're just too large and too clumsy to deal with individual molecules. So what we're going to do is instead of working with molecules here, we're instead going to quantify these as moles. So for every 4 molecules of NH3, I would react with enough oxygen to make 4 molecules of NO. I could then say, well, 4 moles of NH3 would make 4 moles of NO, because I can multiply each of those quantities of 4 molecules times a mole to get 4 moles. So I would get this statement down here. And this is going to look a lot like those types of statements that we wrote with coefficients, where like you had in 1 mole of MgCl2, there were 2 moles of chlorine, for example. This is the same sort of idea, except in these expressions, we're going to get these coefficients right out of the balanced chemical equation itself. So again, you got to have a balanced chemical equation. That's crucial. And then once you have the balanced chemical equation, you can then make these relationships to do chemical calculations in a similar fashion. And that's what we're going to do in the next section. So for this section, we're just going to be writing these types of expressions. Now, you can make any expression between any 2 quantities that you want. So here are all of those. And all I've done here is I have taken some substance and picked another substance to match it with and written an expression for it. I could do that with any 2 that I wanted to. So let me pick, I don't know, let me get a different color here. I'll pick the other 2, and then I'll just write this expression. Either of those work. Or I could do one of the ones that I have already chosen. They don't even have to be on opposite sides. They could be on the same side. So if I do this and this one, then that would be this one right here. So again, pick any 2 and you can relate them together. Now, these are written horizontally. We're going to eventually turn them into conversions by putting something on top of the conversion and something on the bottom so that the units cancel out. Just like we've been doing all quarter in Unit 3 and then again in Unit 12 and 13. Okay, so let's do a little bit of that. Let's suppose I had a reaction that I put 16 moles of ammonia and all the oxygen that I would need to react with it. So I have enough oxygen. We're just not going to worry about it. If I put 16 moles of ammonia in, how many moles of water would come out? So let's go to this screen here and answer that question. We want to leave that expression on the screen as well so that we can see. Oops, that didn't maximize properly. There we go. All right. So I want to turn moles of ammonia. That's not the pen, that's the select tool. I want to turn moles of ammonia into moles of water. Now, according to the balanced chemical equation up there, I know that for some quantity of moles of ammonia, I will also make some quantity of H2O. And I will get those numbers from the balanced chemical equation. So for every 4 moles of ammonia, I will get 6 moles of water. And again, I got that by, I gotta go back to this screen, by taking these numbers here. So now that I know that ratio, I can figure out how much water I make for any amount of ammonia. And the way that we do that is like this. If I take my 16 moles of ammonia, I could then set up my expression to put moles of ammonia on the bottom so it cancels, and we'll turn that into moles of water. Now all I gotta do is put these numbers in the correct spots based on where I got this relationship. So there's 4 moles of ammonia and 6 moles of water. So the amount of water that I would make in this would be 16 times 6 divided by 4, which 16 over 4 is 4 times 6 is 24. So if you put 16 moles of ammonia in, you should get 24 moles of ammonia out. Any questions on how I did that? Let me know in the chat. Now, when you do these types of calculations, again, we're not really going to be working with moles all the time. So instead, what I'm going to be giving you is some other quantity. Almost always that's going to be grams, which you'll have to turn into moles. And then when you get to this part, you would have to turn this quantity into grams too. Now, you should know how to turn some grams of ammonia into moles of ammonia. And then when you get water, you should know how to turn some moles of ammonia or moles of water into grams of water. That uses the formula masses that you can get off the periodic table or from Lentech, where you just type it in and get the molar mass. Okay, so that is more or less where we are going with these types of problems today. Let's do another example just to make sure that we got it. If I have 25 moles of ammonia, how many moles of oxygen do I also need to completely react with it? Now, I still need the equation on the screen, so I got to pull this down a little bit. We'll put this on the screen just in case you want to look at it still. So for the next problem, I want to turn moles of ammonia into moles of O2. What's the relationship between moles of NH3 and moles of O2? Type it into the chat, and I'll write it here. How many moles of ammonia and how many moles of oxygen? It is 5 to 4, just in which direction? Yeah, there you go. 4 moles of... I'll assume that you meant NH3. So 4 moles of NH3 equals 5 moles of O2. And again, we got that from the balanced chemical equation. So now we'll go to my starting quantity here. I have 25.0 moles of ammonia. Blueberry smoothie, huh? That's not a bad place to be. So I'll cancel these units out. Make sure you are writing moles, by the way. Don't just write O2 or NH3 when you do these, because otherwise you'll get confused. You want to make sure that you are explicitly defining the unit that you're working with. So put both the unit, which would be moles, and both the substance, which in the bottom case that I underlined here would be ammonia. All right, now I got to put those numbers in. So ammonia was 4, so we'll put 4 next to ammonia. Oxygen is 5. This one I can't do in my head. It's 125 over 4, whatever that is. 31.25, which is going to round to 31.3 moles O2. All right, any questions, let me know in the chat box. All right, so now I have an unbalanced equation for you here. This is the combustion of glucose. This is what your body does when you consume things that have glucose in them. You then combine it with oxygen that you inhale. When you do that, you produce energy, and you also produce CO2 and water, which you then exhale. So first thing, you got to balance the equation. You're going to get a bunch of the same number, so you'll know if you did it right, because that will be true. And then what I want you to do is answer those 2 questions. I thought there were 3. If you have 24 moles of glucose and all the oxygen ever, how many moles of carbon dioxide did you make? And then if you did a reaction and made 180 moles of water, how many moles of oxygen did you use to do that? Okay, so do these conversions in the same manner that I just did. I'll give you 4 or 5 minutes to do it, and we'll come back and go over the answers. So I'll see you in a bit. say hi? Say hi. Maya had a very important message for everybody, which was she is here. And now class can resume. Alright, looks like we have the equation balance. Yeah, it's a bunch of 6s. Yeah, be careful. O2 it comes as a pair. And then do the calculations there. While I pet Maya, and hopefully she will go away. Not that I want her to disappear, I just want her to not bug me. Hit the wrong key on my keyboard. Okay. Maya has left. I put her out in the hallway, and she immediately came back in, so I had to get the squirt bottle. She knows to leave now. Let's see here. Where am I on the screen? I am here. We can make that smaller. And I can erase all of this. Alright, oh, the first thing we gotta do is we gotta balance the equation. So, let me do that really quickly. That's the wrong pen. So I got 1 of this, and then 6 oxygen, CO2, and H2O. Alright, so for the first one, I have moles of glucose, C6H12O6. And I want to turn that into moles of CO2. And I know that the relationship between these two is that for 1 mole of glucose, there are 6 moles CO2. So for every mole of glucose you eat, you have to use a lot of oxygen. And you make a lot of CO2 just by respirating. Fortunately, a lot of the atmosphere is oxygen. There's tons of oxygen, so there is more than enough. All right, so I have 24 moles of glucose. And we'll turn that into CO2, as you do. So those units cancel out. I now have the units that I want for my answer. So now we can run the numbers. For 1 mole of C6H12O6, I also produce 6 moles of CO2. And I get 24 times 6, which I believe is 144. 12, 24, 140. Yeah, okay. I'm trying to do this without my calculator. Probably should use the calculator, but you know. Whatever. All right, that's the first one. For the second one, I can turn moles of H2O into moles of oxygen. And the relationship between those two is that for every 6 moles of water I make, I need 6 moles of O2. And you're going to notice that, oh, well, whatever I put in is what I'm going to get out here. 180.0 moles H2O. When I set up the units, I put moles of H2O down here so it cancels. Moles of O2 so that we get what we're solving for. And if I have a number divided by itself, well, those numbers just cancel too. We don't even have to put that in the calculator. There you go. So that's how you do these types of problems. So those are the easy intro problems that are just designed to get you to work with this concept. In the next section, what we're going to do is we are going to use those numbers, but we're going to start with grams instead, or we're going to start with particles instead, or whatever. So that's where we're going with this. Now, something interesting that happens when we do these calculations is that they work out to follow the law of conservation of mass, which of course they should, right? We're doing chemistry. We're not creating or destroying matter. So as long as the equation is balanced, the mass of the reactants that you put in should equal the mass of the products that you get out. So if I were to turn these moles into masses, both sides should be the same amount. We're not going to do an example of that. I'm just going to show you this. So for this reaction again, if I turned each of these moles into masses, here's what I would get. So 4 moles times 17.02 grams per mole. So that would be ammonia. We'll just highlight these different colors here. So we'll do this first one in yellow. So here's ammonia. Here's its mass times the number of moles. And we'll do the same thing for oxygen here. Remember, it's O2, so it's 15.999 times 2. That's how you get 32. That left side should equal the right side, which would be these two things. So here's NO. And here is H2O. Now, if you did these calculations, what you would find is that the numbers on the left and the numbers on the right work out to be this. Now, there is a little bit of error in there, but you'll notice that for the calculations that we did, if I treat 4 as an exact number, and I multiply by 17.02, I should only get 4 sig figs. But remember that if I do addition 17.02 4 times, that's the same as multiplying by 4, right? And then I would get 5 sig figs. So our answer is going to be within error if it was 4 sig figs, because these would both round to the 10th place. So, in other words, what we get at is the result is close enough. And so we have satisfied the conservation of mass. We've verified it by doing this experiment. You can do this with any reaction you want to. And what you'll find is that the mass that you put in is what you get out. So it's nice to see that the numbers check out at the end of the day and match up with the concept that we were talking about in an earlier unit. All right, so let's actually start working with these things in masses. So there is a special term for this process, and that term is called stoichiometry. Stoichiometry is just the practice of converting masses of a reactant into masses of a product by using this mole to mole ratio. And we're going to use that little chart that we had before where we would turn grams A into moles A, into moles B, and so on. And like I said before, it's kind of the whole point of this class. So we're going to be working with masses in the lab because that's what you weigh. You put it on the balance and you get a number, so that's how much mass you have. Since you know the amount of mass you have, you can turn it into moles. And if you know how many moles you have, you know how many moles of product you can expect. So let's do an example of this. So the first thing that we're going to do is we're going to do the reaction of sodium azide when it decomposes, and that's this. Now, just in case you're curious, let me clear this screen. Sodium azide is a substance that we use in your automobile. So let me draw my automobile. I have a Jeep, so it means I drive in a giant cube. There's my wheels. And inside the Jeep, which we'll draw in green, there is a steering wheel and a steering column that connects to a region that is connected to your bumper. And let me actually make this all like a tube here. There we go. Something like this. And inside this little compartment here is sodium azide. Now, the sodium azide is hooked up to a circuit. And what the circuit does is that when you impact something with your bumper, it completes the circuit. And it causes the sodium azide to decompose into, and I believe it's 2, 2, and 3. Yeah, I could just look at the expression on the board there. This is a solid. We don't really care about it. But this is a gas. And it makes gas really quickly. So this gas then fills the container in here. And since this is all connected, it fills this too. And it fills all the way up to the steering column where there is a bag, and the bag goes foomp and fills. Hopefully maybe not that much space, because that would be the entire seat. I would be displaced. But the nitrogen that you produce fills the airbag. And it does it really, really, really fast. If you've ever been in a car that has an airbag, every car has an airbag nowadays. When I grew up, this was actually a new thing. If you bonk into something and the airbag goes off, it inflates really, really quickly because this reaction is very, very quick. Okay? So what we're going to do is we're going to answer some questions about this. Say, oh, here's how much sodium azide I put in your car. How much nitrogen in grams can you make out of that? So the first question I want to ask is, okay, I'm going to put 20 grams of sodium azide into the automobile. How many grams of nitrogen do you get out of this process? Now I'm going to go like this for a second. And I am starting with a quantity of N2 in grams. And I want to figure out, oops, no, I'm not starting with N2. Hold on. Back one step. It's not working because, of course, it's not. There we go. I'm starting with that mass, and I want to figure out how many grams of nitrogen I get out of it. Now, I can't just convert directly. I need to turn things into moles. Remember that I can only convert from one substance to another when they are both in moles. But I can convert between moles and grams easily enough. So on our chart, we would be doing something like this. So let me get a better color here. So I'd start with grams of... Ooh, that's not a good color. That erases everything. You know, we'll just circle. We'll do... That's the wrong color. There we go. So I would start with this mass. I would then turn it into moles. Turn that into moles of the other thing, which is nitrogen, and then turn that into grams, and we're all set. So let's do that. Let's first do this just to get some more space to work with. Oops, that was a little too much. All right, so where did half of my thing go? Maybe it was undoing and I didn't realize it. We'll put that back. That's not right. There we go. All right, so according to our chart here, we're going to turn grams of ammonia or grams of sodium azide into moles of sodium azide. So we'll set up the units to do that. Grams of sodium azide, moles of sodium azide. Then the next unit would be to turn moles of sodium azide into moles of N2. So we got that. And then the last step would be to turn moles of nitrogen into grams of nitrogen, as we see here. Now we just have to look at these relationships. These both involve grams turning into moles, so we're going to go look those numbers up on Lentech, and somebody already did that for me. So 1 mole of sodium azide is 65.01 grams, because I added a sodium and 3 nitrogens. This one over here, 1 mole of nitrogen, is whatever it is on the periodic table times 2. So that would be 28.014, which I'll just write as that. And then finally, this one in the middle here is the step that we were just doing in the previous section. I can relate moles of something to something else by looking at the balanced chemical equation on the screen there. And so I look for sodium azide. I use 2 moles of sodium azide, and I get 3 moles out of nitrogen. And so I punch all that in the calculator, and what do I get? So 20.0 times 3 times 28.01 divided by parentheses 65.01 times 2. And I got a different number than you did, Kyle. Double check what you punched in the calculator. I got 12.9 grams of nitrogen. Well, I'm questioning the way that you did it then. You might have a mistake. So again, these right here, these steps were molar mass. from the periodic table. And then this one right here was from the balanced. I don't know what I'm writing here. Balanced chemical equation. Okay? That's how you do stoichiometry. You want to do the problems just like this, where you set up all the units and then do the calculation. And you want to do it this way every time because we're going to build off of this in later sections. We're going to use this information to add other features to it, such as molarity, which is concentration. That's the whole of Unit 16. And we can do other things like density. So I could say I give you a gallon of gasoline. Here's the equation for combustion. How many grams of CO2 come out of a gallon of gasoline after it's been combusted? So what you'd have to do is you'd say, okay, I know a volume. I got to turn that into liters because we're only going to do metric. You'd use the density to turn that into a mass. And then you'd use the mass to do this process. So everything we've done all quarter now sort of comes together here. We're going to put it all together. What did I just push? I hit the wrong screen. There we go. All right, let's do another example here. Are we going to do stuff with the STV? We don't do gas laws in 140. We do gas laws in 160. I have to think about that. 162, I believe, is when we do gas laws. Well, I would not do it the silly way, so I would definitely do it the way that I showed you, because I can't guarantee what you did will work every time. The method I'm showing you on the screen, though, will work every time, provided you put all the conversions in correctly. All right. For this example, we're going to do a micro experiment. I'm going to take a really tiny quantity of sodium azide and see how many molecules of nitrogen you get out of that. So same process here. But this time, instead of ending with grams of nitrogen, we're going to end with molecules of nitrogen. So we'll start with grams of sodium azide. And I want to know molecules of nitrogen. Remember that molecules are like particles. So we're going to turn this to moles. Always got to start by turning it into moles. Then we'll turn moles of sodium azide into moles of nitrogen again. And then we'll turn that into molecules. So let's start with the quantity that we have. 1.86 times 10 to the minus 6 grams of sodium azide. We'll turn grams into moles. And because this is the same experiment, we're going to get the same number in this spot that we did last time. Then what we'll do is we'll take moles of sodium azide and turn that into moles of N2. So that those cancel out. I ran out of space, so we'll go down here. We'll then turn moles of N2 into molecules of N2. And that'll give us the answer once we filled in all the numbers. Now, this first one is just periodic table again. So in a mole, there are however many are on the periodic table. I've already forgotten the number. It was written in the chat. It was 65.01. This number right here is just the balanced chemical equation again, which is the same as last time. It's not on the screen anymore, but that's okay. We remember it. And then lastly, this down here, well, in a mole of anything, how many molecules are there? That's good old Avogadro's number. So we throw it all in the calculator. 1.86 times 10 to the minus 6 times 1 times 3 divided by parentheses 65.01 times 2. And the number that I got was 2.58 times 10 to the 16. So even in this itty bitty tiny amount of stuff, we have like 1.86 micrograms. You still make quintillions of molecules. Or quadrillions. I don't know. We make a lot of molecules. Did I write the wrong number on my calculator? I might type the wrong number into my slide. My slide says 2.53. When I go back here, I might have read the wrong number when I did that. So let me edit that real quick. So 8. And then when I go back here, uh-oh. There we go. I broke the slide. Oh, I just noticed that this doesn't line up in the right spot either. I didn't fix that. Give me just a second here. Oh, I didn't intend for that to disappear, but... Just a second. There we go. That does what it's supposed to. So I apologize. My little diagram over here. Do I have a marker? Yeah. This right here had the wrong orientation. So I have fixed that. Is it raining outside my place? Let's see here. No, I don't have any rain. Just wind. Not even that really anymore. It was very windy earlier. Oh, no, I have a little I have teeny rain. Just a little. Oh, did I put 1.86? I did. Oh, look at that. Okay. Well, now I gotta fix this. Hold on. Ah! Sorry, it'll blank out again. Boop. Okay. So if I do this... Oops, that's... Oh, calculator, what are you doing to me? Oh, entry. There we go. That's what I want. So I want... That's a 2. That's the 2.53. Yeah, okay. Now I have the correct number. Oh, I gotta fix that down here, though. Sorry about that. The process is correct. I just can't copy numbers because I am bad. Oh, you can't even see what I had fixed there. There we go. So now this up here is correct, this 2, and that gives me a 3 down here. All right, let's go do another problem. All right. So for this problem, I didn't give you any equation. I just said 5 grams of nitrogen reacts with hydrogen to make ammonia. And tell me how much ammonia you make in grams. So we're going to have to make a balanced chemical equation just to even do the reaction. So this is going to be sort of our let's put it all together problem. So let's put it all together. So we have to take the information in the problem, and we need to make a balanced equation for it. So first, let's write the equation. So I'm going to react nitrogen with hydrogen to make ammonia. Because that's what the problem says, so that's what we're going to do. Now I got to balance it. So I got 2 and 2, 1 and 3. Now, by now, everybody should be pretty proficient at balancing equations. And so we can start to do the more advanced sort of techniques rather than just putting in numbers and guessing. So whatever I enter in this space here and whatever I put in this space, they're going to be related through hydrogen, right? So if I want the same on both sides, whatever goes in this blank times 2 should equal whatever goes in this blank times 3. So I'm going to do this because I know that will get me 6 on both sides. Now, the side effect is that that's going to affect this nitrogen here, but that actually works out in our favor. And even if it didn't give us a 2, we could have put a different number here to fix that. So I was able to determine that by multiplying those two numbers together and saying, oh, I know what they'll both equal. So now we have a balanced equation. N2 plus 3H2 makes 2NH3. And that can save you a little bit of time. So now that we have that, let's make our little stoichiometry chart. So we're going to do grams of nitrogen. And I want to figure out the mass in grams of ammonia. There you go. We'll just do this. Okay, so let's do the calculation just like we've done these already. So not 500. Of N2. We're going to turn grams of N2 into moles of N2. Then we'll turn moles of N2 into moles of NH3. And then we'll turn moles of NH3 into grams of NH3. We're just following our little chart, just like what you did with the previous problems. So now we got to look up our relationship. So grams to moles means we look up something on the periodic table or on Lentech. N2 is 2 times nitrogen, which would be 28.01. Because each nitrogen is 14.007. Times 2 gives you this number. I'll do the same thing over here with this one. 1 mole of ammonia is nitrogen plus 3 hydrogen. That one I don't have memorized. It's 17 something. Plus 3 times 17.03 is what I got. And then for moles to moles, we use the balanced chemical equation. So moles of N2, that's up here. That's 1. And then moles of ammonia, that's 2. All right, do the algebra. 5.00 times 1 times 2 times 17.03. divided by 28.01 times 1 times 1. And I get 6.08 grams of ammonia. Now here's a question for you. If I put 5.0 grams of this in, and I got 6.08 grams out, did I violate the conservation of mass? Because what I put in and what I got out, those aren't the same number. How come? What are we missing here? Yeah, we're missing the hydrogen's mass. How many grams of hydrogen do you think were used in the reaction? Without doing the stoichiometry, because we're going to do the stoichiometry in just a second to confirm it. But just by using the conservation of mass, what number do you think we get? Yeah, 1.08. So that must be true, right? Let's check to see if that's the case. So what I'm going to do is, if you're still working on this, you should pause the video, but we're going to erase this part here. Get rid of all these odds and ends here. And instead of turning it into moles of ammonia, we'll turn it into moles of hydrogen. And so for every 1 mole of nitrogen, we make 3 moles of hydrogen. And 1 mole of hydrogen is 2.015, I believe. Actually, I believe it's 6 now that I'm... There we go. So I'll punch that in the calculator. 5 times 1 times 3 times 2.016 over 28.01. And wouldn't you know it, the number that the calculator spits out is exactly what you would expect it to be. So we have verified the conservation of mass in 2 different ways. Now, which way should you use on an exam or question like that comes up? So if you were doing this at work and you put in 5 grams of nitrogen, got 6.08 grams of ammonia out, it's pretty easy to say, oh, the difference must be hydrogen, and subtract. And then just hand that number off to the next person. That'll save you time, and that'll increase your efficiency. So both methods work. In general, though, you will need to do stoichiometry to do at least one part of the problem, and then you can figure out the rest of it by using conservation of mass. So it's just another tool to have in your back pocket if you need it. All right, so what we're going to do is we're going to do these problems. We're going to do more of these. I have another one, I guess, for you. We're going to take a break because it is our hour mark. So let me put this up on the screen. I need my live split. There it is. So we'll do this, and I will go put more creepy Resident Evil music up. And I'll see you in about 10 minutes. So we'll see you in the end of the break. There we go. Okay. Some of these Resident Evil tracks are just kind of like background noise, apparently. There we go. All right, I hope everybody is back. 10 minutes is not enough time to do your dailies in WoW. I'm not playing WoW, but I do know that an expansion released yesterday, so that's exciting. What are you doing here at lecture when you can watch this later, right? All right, so we're going to do this problem. I'm going to just write the balanced equation on the screen for you, but what I'm going to do is I'm going to have you try to do this problem. So N2, 3H2. Actually, what I should do, yeah, it doesn't appear. So we've already done that. But what I want you to do is to use 2.75 grams of H2. Tell me how much N2 is also needed in grams, okay? So follow the process that we just did on the previous examples and calculate the amount of nitrogen that you need for this process, okay? So I'll give you 4 or 5 minutes to do that, and then I'll go over the answer when we get back. Okay, see you in a bit. I don't know the answer. Let me find... I could just hit the button, I suppose. So here's the answer. I got 12.8 was what I got. I'll leave that on the screen, let people keep working. Try and find where you made a mistake. If you got 12.7, that's close enough. That means you did it correctly. Yeah, if you got that, you're close enough. I gotta clear this screen. Let's go over the answer. And show how to do the calculation. Why do I have this symbol? Okay. It's giving me a loading icon, and I was like, Alright, so we've got grams of H2 to start. We want to get to grams of N2. We'll turn that into moles of H2 and moles of N2 to get to grams of N2. Alright, so 2.75 grams H2 is our starting quantity. We'll turn grams of H2 into moles of H2, just like the chart says. Then we'll do moles of H2 to moles of N2. And then we'll do moles of N2 to grams of N2. And then we just got to put in all the numbers. So in a mole of H2, there are 2.01, was it 6? Yeah. According to our balanced equation, there's 1 N2 for every 3 H2. And for N2 in 1 mole, there are 28.014. Probably don't need that many sig figs, but that's okay. When I punch it in the calculator, I get 12.7 grams of N2. What does this slide say? 12.8? That's close enough. I probably used a different periodic table at the time. Good enough for government work. All right. Do I have more of these for you to try? I think I have a few more. And let's see here. Oops. There we go. Yeah, so I got two more. So if you are aware of the substance fool's gold, that's what this is. Fool's gold looks just like gold, except it has a major difference that gives it away. And that difference is, well, it's an ionic compound, and ionic compounds tend to form cubes or very flat surfaces. So if you see real gold looks kind of an amorphous lump. Fool's gold looks just like gold in color, but it has these very rigid cubic shapes to it. So fool's gold is iron 4 sulfide. When you burn it with oxygen, you get iron 3 oxide and SO2. Balance the equation as shown on the screen, and then answer the two questions related to fool's gold and the quantity that I gave you, 38.8 grams of it. Tell me how many grams of SO2 you can make and how many molecules of iron 3 oxide you can make. Okay? So give these problems a try. We'll come back in a few minutes, and we'll go over the answers then, and then we'll go on to the next topic. All right, 1 or 2 more minutes to finish up. Looks like we have some answers coming in. All right. So let's go over the answers. So we'll clear this off the screen. So first we have to balance the equation. Let me do that really quickly. So let me get rid of where it says fool's gold. Boop. Let's see here. 3, 5, 9. So that's 10, and this would be... Oops, that won't work. Hold on. So 2, that makes this 4, 8, 11. So then this becomes 4, 2, and then 8. All right. Did I do that right? I'm trying to do this really fast without having to write the whole inventory. 4 iron, 8 sulfur, 22, 16 is 22. Yep, that looks good to me. I'm on the wrong screen. There we go. Let me know if you got something different for your balanced equation. We'll just do this. All right, how many grams of SO2 are produced when 38.8 grams of FeS2 are combusted? So we got grams of, that's the wrong color. Grams of FeS2. And my goal is grams of SO2. So again, we'll turn stuff into moles. Get the moles of the thing that we want. Should be a 2. All right, there we go. So 38.8 grams FeS2. Set up the units so they cancel. And then follow the chart to turn units in from one thing to the other that you want. Then we'll do moles of FeS2. We'll turn that into moles of SO2. And then finally, moles of SO2 into grams of SO2. And that's what we want to do with that. Now we'll go back and fill in the numbers. So in 1 mole of FeS2, there are, I don't have the slightest idea. So Lentec, where are you? It's the first thing that pops up when I type the letter L, so you know that I use this a lot. 119.98 is what I got. For that, for our balanced chemical equation here, FeS2, there are 4 moles of that for every 8 moles of SO2 that we make. And then SO2, I believe it's like 64 something, right? Let's type that in. SO2. 64.06. Again, that's off the periodic table. Again, that's a cat. Hi, Maya. Let's punch that all in the calculator. 38.8 times 1 times 8 times 64.06 divided by parentheses 119.98 times 4 times 1. And I got 41.4 grams of SO2. Maya, please. I'm working. All right, looks like some people got that too, so that's good. Let's go on to the next problem, which I need to actually put on the screen here. How many molecules of iron 3 oxide are produced from the same quantity of FeS2? Let's just scroll all this off the screen here. So we're going to start with the same quantity of FeS2, and our goal is molecules, which actually it should be formula units because this is an ionic compound of iron 3 oxide. So I'll put the correct thing on there. But we're going to turn from grams into moles. We'll then do moles of iron 3 oxide. And then we will squirt bottle the cat. You got to stop meowing. You can't do that. Sorry, it's really hard for me to focus when I hear meow, meow, meow. Even with a headset on. So we'll set up the units in exactly the same way as before. This time we're going to be following this flowchart instead. And then once we got to moles, Fe2O3, we'll get to formula units, or funits, I guess we'll call them. All right, so in a mole of Fe2 or FeS2, there are still however many there were before. What was that? 119.98. I just realized I was off the screen there. I apologize. Should be able to see it now. Moles FeS2, according to the balanced chemical equation, there are 4 of these and 2 of those. And then in a mole of anything, there are Avogadro's number of particles. So we get 38.8 times 1 times 2 times Avogadro. That's the wrong button. There we go. Divided by parentheses 119.98 times 4. 9.74 times 10 to the 22. And I think that does it. All right. Any questions on how we did these? Let me know. You can drop a line in the chat or you can send me an email. I overestimated how long, or I underestimated how long it would take for us to do this. So that's where we're going to stop, I think. Now, what we're going to do for the rest of Unit 15, we're going to finish this up on Tuesday next week and then move on to 16. What we're going to do is everything that we did today, but add an extra little twist to it. So in these problems, what we've done, specifically, like, say, the problem that we're doing right now, that's currently on the screen. How many molecules of Fe2O3 are produced from this amount of sulfur? We've sort of made an assumption. And so the assumption is that I have put in some amount of FeS2, and that amount was 38.8 grams of this. But in order for the reaction to go, I need to put this in, right? For this specific problem down here that we've been doing, the amount that I have put in here is infinite. I have put all the oxygen that I need, and I'm not even going to worry about it. In the real world, you don't have infinite quantities. Now, you can put a ton of stuff in and assume that it's in excess, but most of the time, that's not very cost efficient or even equipment efficient. Or maybe the stuff is just not very, like, abundant. You just don't have much of it. So instead, what we do is we put in limited quantities of both. And one of those things will run out first. The other one is the one that's in excess. But you don't know when masses are given. So what we're going to do for the next section is what's called the limiting reactant, which is I give you quantities of 2 reactants, and you do the stoichiometry twice. And you figure out which one makes less, because that's the one that the reaction will stop at. Because for each calculation we've been doing, we assume the other one is in abundance. It doesn't affect the calculation. The one that limits it is the one that's written in the problem. So in this problem down here, you can't see me underlining that because it went off the screen. FeS2 limited my calculation, and then O2 was abundant. There was excess of it. But suppose that I gave you some mass of oxygen. Then you'd do the problem twice. You'd treat it the first time with the mass given and that the other thing was in excess. And then you do the problem with the oxygen's mass and treat the other thing as an excess. And see which one makes less. That's the premise behind the limiting reactant. So if you're reading the text over the holiday break and you're like, oh, I don't have any idea what the hell's going on here, come back to this lecture at the very end where I just briefly talked about it, and hopefully that'll get you on the right path. But that's where we're going to go. Once we get back next week, there's also an exam coming up after week 11. Not this weekend, it's the next week, so don't worry about it yet. But that's about it. So I will hope everybody has a good week off. Make sure that even though we aren't going to be meeting for class tomorrow or Thursday, that you put a little bit of study time in when you can. And make sure you get that quiz done by Monday or Tuesday if necessary. And keep working on Lab 4 so that you stay on top of these calculations, because they never really go away. Okay? Have a wonderful break, and have a happy Thanksgiving, and stay safe. I didn't prepare the little musical thing, did I? No, I didn't. Hold on. There it is. Have a good one.